Okay, our next speaker is Colin Gordon, and he's going to have a follow-on talk on error localization.
All right, thank you. So, all right, I'm going to talk about error localization for a different class of analysis for this thing called sequential effect systems. I'll explain what that means exactly. This is joint work with my PhD student Chaewon, who unfortunately couldn't make the conference this year, but hopefully you'll get to meet her in the future. I'm thinking about this in the domain of effect systems, which are these extended type systems that track not just sort of input and output, shapes and operations for functions data, but also what kinds of behaviors might the program exhibit internally as it's executing. The classic example, of course, is Java's checked exceptions, right? So if you throw something in Java, and you either don't catch it and you don't declare that you're throwing it in your method annotation, you get a complaint. So that's a simple, familiar example for most people. But this goes well beyond that to things like what regions of memory are you accessing, what locked data are you potentially accessing. And these are typically modeled in the literature with join semilattices. So some set of behaviors, and you can over-approximate by taking least upper bounds, and that gives you a partial order for subsumption. And we end up with type rules that look like this, where here I'm using these chi symbols, and I'll use that throughout to talk about some abstract behavior, some abstract effect of a program, where in general, if we think about checking, is the behavior of some unit of code, like a function or method, consistent with an annotation, we basically check, is the overall effect of this method body consistent with its signature? And then whenever we look at actual pieces of the program that have multiple subcomponents, we basically just take the least upper bound of everything that's happening there. So we take the least upper bound of the effect of computing the function term, computing the argument term, and then computing whatever computation the body of that function performs. And what's interesting here is actually, even though this theory is very nice and useful, and this is how people generally present this work, this is actually not at all how people actually implement the systems. They do something quite different. So if you were to directly implement exactly what these type rules said, you would basically just take the least upper bound of every small operation in the entire program, and then at the very end, you would do one bounds check. Is this less than the bound we wanted? So if you were doing this for Java's checked exceptions, you'd basically say, okay, we collect all the things this method body might throw into some set X, and then we check at the very end, is this less than the throws clause? If we say throws Y, is it less than Y? This, of course, yields pretty useless error messages. And the reason for that is because if you can imagine, you have something like 700 lines of code. Somewhere in there, you throw a particular exception that is not supposed to be thrown according to the throws clause. If you get an error message that's basically, well, if we collect all of the set of exceptions thrown anywhere in the 700 lines of code, this is not a subset of what you said it threw, it doesn't really help you find the source of the error, right? In this particular example, you could grep for throws and find it, but if that was hidden behind calling another method, it would be significantly harder to debug. Because there's no information in this coarse-grained comparison about where the error lies. So what people do instead is what I'll characterize as local. So they figure out an equivalent way of checking the same rules, but with a bunch of many, many local checks instead of one global check. And the intuition here is, of course, that they basically check for every individual action of the program and every method that it calls, is that individual program component's effect less than the bound. So if we have some function like this that says, okay, well, we're allowed to throw exceptions A, B, and C, and it goes through and says, okay, does A throw something in ABC? If we assume A throws A and B throws B, this goes on and it's fine. It can check, okay, A throws A, that's in the set, great. B throws B, that's in the set, great. And this lets us get good error messages, because if it gets to D and D throws some exception D that's not in this set, it can say, well, it's this call that's the problem, it's not vaguely somewhere in the method. And this works because of this property of joint semilattices, which is this universal property, right? That in order for some join of some large set to be less than a bound, every individual thing in the set has to be less than the bound on its own, right? And so there's this nice algebraic connection between this global view that's very convenient for working out theory and designing analyses, and this local implementation that gives much better error messages. So we're interested in doing this for a slightly broader class of effect systems called sequential effect systems. You might have heard these also called flow-sensitive effect systems. The terminology started kind of fluctuating about 10 years ago. So Java's checked exceptions, of course, are not flow-sensitive. If you throw A and then maybe throw B, or throw B and then maybe throw A, it's the same effect. It's the same set of possible exceptions thrown. But if you want to start talking about some behaviors over time, like are you acquiring a lock and then releasing it, or are you releasing and then acquiring? Because those are not the same behavior. They're not interchangeable. Or if you want to worry about the order of security-sensitive operations, are you checking for authorization before you release data publicly instead of the other way around? We want to be able to reason about that. Or more broadly, many of these can be characterized in terms of sets of finite traces, which turn out to also form an effect system in certain models. So the literature here is a little more varied than for traditional effect systems. Traditionally, it's, like I said, almost always a joint semilattice. There's a lot more proposals in play for sequential effect systems. I wrote a paper a few years ago that has a survey if you want to see the full menagerie. But we're going to use this particular model I proposed, not just because I proposed it, but for technical reasons you'll see in a second, where it's called an effect quantale. And the idea is we have a structure on the set of effects E that has not just a least upper bound. So we still have a joint semilattice in there. We still need to be able to over-approximate. Well, we don't know which branch of the conditional we're taking, over-approximate both. But we also have a monoidal structure in there for sequencing. So this sort of right triangle symbol we say is sequencing. And so if we have A sequence B, it means we're reflecting the fact that the behaviors in A happen before the behaviors in B. They precede it in evaluation order. There's some additional conditions in there. You'll notice the word partial here, and other parts of the talk. If you want to tune out the word partial, you can. There's one place later where it's important, and I'll point that out. And there's some laws for how these interact. So sequencing distributes over join, and we have other nice algebraic properties there. The real reason this is useful for us with an eye towards building real tools, though, is because there's also been work on using, from this structure, you can derive iteration operators to deal with loops, to deal with fixed points, and also support for non-local control, like early returns, exceptions, and other things that happen in real languages. Also, as a special case, it captures the traditional regular effect systems as well. If sequencing is just also join, then it happens to also be commutative, and you get all the same results you would care about. In this setting, the type rules shift then a little bit to take advantage of these rules. So this is the rule for calling a function in a sequential effect system. We've switched from taking joins of everything to actually reflecting the behavior of the function happens before the behavior of reducing the argument, before you actually invoke the code, since that's the evaluation order for left to right, call by value. There's also a little shift in when we allocate a function. Instead of it being the bottom behavior, it's actually the unit for sequencing, right? Because unless you're in the narrow domain of reasoning about memory allocations of closures, it's generally not an effect we care about, but it's otherwise similar. So what we'd like to do for this richer model of program behaviors is figure out how do we implement these and get good error reporting. So in prior work, there's basically two approaches people have taken. One is sort of what I said was the bad approach for traditional effect systems, and it's still bad if you do this for these sequential effect systems, and that's you just compute with all of these operators based on the type rules, a big expression with sequencing and joins, and then you compare it once at the end to some annotated bound on behavior. And you get bad error messages with this for the same reason as before, except maybe even worse because the algebra is a little bit harder to think through. The other alternative, the other thing people have done is they've used type inference, right? So basically generate a bunch of constraints based on what it would take for a program to be type correct and effect correct. And then these get handed off to a constraint solver that works through them in some convenient order to reach a conclusion. And this is better, and it will give you local errors, but it also is a little bit unpredictable in the sense that if you just hand this off, in general, when you do constraint solving, you don't know what order the constraints will be solved in. If a constraint ends up being violated, it may or may not be an actual constraint related to a mistake, or it may be that your mistake propagated some weird information to a distant, unrelated constraint. So sometimes you get good error messages, and sometimes you get weird error messages. And there's lots of general work in this space of how to improve error reporting for type inference in general. It's still a little unpredictable, but it's still lively. There's cool stuff happening. There's a paper later this week at UPSLA I'm excited about. But for this domain, it doesn't solve the problem. We don't get precise error messages. So what we really need, we need something like what we have for the joint semilattice case, where we have some algebraic shift from looking at things as a global check over the behavior of all the code in the method against some bound, to some local checks that we can use to give more error-precise reporting. So what we're trying to do is come up with a way to relate a local and global view, and historically, there has been no local view for these flow-sensitive effect systems. So the key ingredient turns out to be this idea that has a rich history in the mathematics literature called residuated semigroups. So I'll preface this by saying I'm going to ignore a couple subtleties that turn out to be important for like actually building a tool and making this work for the full effect quantales theory. But the presentation in the paper is a direct refinement of this, so this is the core key idea. And I'll also note that there's a subtlety that's easy to overlook, which is that while this solution applies, we can define what I'm going to talk about for most effect quantales, and certainly all of the effect systems I'm aware of in the literature. It doesn't follow from the axioms for an effect system that I'm working with. So it is possible, though we're unaware of any counterexamples, it's possible there are some effect systems this won't work for, but we haven't found any yet. So the core idea is this idea from mathematics called a right residuated semigroup, right? And so that's a bit of a mouthful. And the idea is basically you take a partially ordered semigroup, which you'll notice that I'm consciously using notation that's basically the same as the effect quantale notation because they're basically ordered semigroups. And there's this one new operation, this backslash, which is partial. So it's partially defined. So this is the one that's important to know as partial. And when it's defined, it has this interesting property. So if we are, say, checking a method body and we are looking at the relationship between some prefix of method execution, characterized here by y, and some rest of the method body x, and we want to compare this to some upper bound like a throws clause z. On the right here, we have basically the global characterization of, well, we have these two expressions, they're executed in order, we sequence them and compare them to the bound. And then on the left, we get this different relationship. So this slash operator, this y slash z, is basically if your ultimate goal is behaviors characterized by z, what's left if so far you've done y? And so this constraint says that basically if we want y followed by x to be less than some bound, in order for that to be true, x just by itself has to be less than whatever you have left after executing y. So I know this is still a little bit abstract, and we'll get into details very, very quickly. But there's a couple, just general note, if you fill in some of these details that deal with a couple extra quirks of effect quantales, this core idea carries over to effect quantales, and that's sort of the key technical development in the paper. So I know this is still very abstract. The key thing to retain from this slide is y slash z is what's left to do in z, if z is the final goal, after you've done y so far. So as you're going through execution of a method, if the things you've looked at so far have behavior y, and your final goal is z, this residual is what's left. Right? What are you still allowed to do? And this gives us the local view of checking that we actually need to give localized error reports. So if we're just doing two expressions in order, we're not doing application now, it's just we're running one expression, then another, they just happen to be evaluated in some order, and their effects are Chaewon and Chi2. If we take that law from the previous slide and push this forward, then in order for sequencing those things to be less than some method bound, then it has to be the case that if you take that method bound and take the residual with the first expression's behavior, that still has to be greater than the second expression's behavior. So this now has shifted us from a bound on the larger expression to a bound on just the second expression's effect by itself. And this is actually important because there's two things going on here. There's two important constraints. One is that this residual has to be defined. So it's possible for this to not be the case. For example, if you've already done too much, right? So if we did take this with the special case of treating traditional effect systems like this, as if they were sequential, if it says, you're allowed to throw A, B, and C, and you've already thrown Q, you're out, right? The residual will be undefined because there's nothing you can do to sort of take back that Q later. The other thing is that it also gives us this upper bound on what's left. So if the type checking algorithm examines things in sort of top-down, line-by-line program order, at some point we have an effect for a certain amount of the code in the method, and we can use that and the upper bound to give a tighter bound on the rest of the method that hasn't been checked yet. So this ends up being, in a recursive type checking algorithm, we take this upper bound and we continue taking residual as residual as we visit more and more and more lines of code. And this basically narrows down possible behaviors for the rest of the function as well. So if we have a program fragment that just does two operations, like call B, call C, if we're doing this with finite trace effects, where these are some maybe security sensitive operations, we want to see, are we following a certain prescribed protocol of doing these things in order? If the target bound, the things we're supposed to do are, first you do A, then you do C. This is enough for us to flag B as the problem, rather than just saying the whole method is wrong, because the residual of AC minus B is going to be just undefined, right? If you're supposed to do A and then do C, but you've done something unrelated instead, there's nothing you can do later to get back to having done A and then C with nothing beforehand. You've already kind of done too much. So that's the key idea, and the paper goes on and develops this with a little more nuance and dealing with some of those additional subtleties I said I was sweeping under the rug for a type lambda calculus. Describes the type checking algorithm in detail, proves the checking algorithm is correct and sound for a type lambda calculus, and in particular that it gives the earliest statement in program execution order at which it's clear that you've already made a mistake. And we'll see an example in a slide or two. It describes a full implementation of this for Java, building on some of those constructions I mentioned for effect quantales earlier, so that's online. And then it shows examples, like we'll look at in a moment, of doing this for a couple concrete sequential effect systems. So one of the, sort of from a historical standpoint, earliest, like well-known flow-sensitive effect system is this system from Flanagan and Kadir from 2003 that deals with atomicity. So in a concurrent program, you might call a block of code atomic if its execution is indistinguishable from, if other threads cannot tell the difference between that unit of code executing all as one with no interruption or interleaved with actions of other threads. And so the idea, I won't get too far into the details, it's built on this theory of movers from Richard Lipton in the 70s, but the idea is basically every action in the program gets labeled with how it would commute with respect to actions of other threads. So there are actions that commute both directions, like you assigned a local variable. And there are actions that commute only one direction, either only later, like acquiring a lock, or only earlier, like releasing a lock. And if you can sort of commute all of these things together into one big block, you can say it's atomic. That's the idea that's trying to be captured by this sequencing operation here. So they implemented this for Java back in 2003, and they found a bunch of atomicity bugs in Java 1.4. So one of the secondary reasons this paper was important is because it was one of the earliest papers on this class of concurrency bugs as well. But there's actually no information in the paper about what error reports look like, and kind of reading between the lines, it seems that they basically did bottom-up, which is the direct thing to do if you have sequencing and composition and least upper bounds. But, all right, where'd that go? Still down here.
Happens twice already. We checked the tables, so I'll be back in a minute.
All right, well, I'll say a few words more, but won't. There's another slide that actually has concrete example of checking this for a Java program. Long story short, we've implemented this for Java, as I mentioned a second ago, and with a little bit of deep Googling, we managed to find the JDK 1.4 sources, and with a little creative massaging, we managed to actually run our modern tool on the JDK 1.4 sources, which actually took some work, but was not actually as bad as I was afraid. And then basically, among other things, so we ran this on some new examples as well, but we also re-implemented this system I was just talking about for Java in this modern framework and ran it on this old JDK 1.4 code to see what happens when we tried to give error reports for these known bugs. So the results, as you might guess from the fact that the paper was published, were good. You may have to use your imagination with the penultimate slide of my talk, which was actually the code example. Aha, okay, thank you. Yeah, so here's an example. This is code from JDK 1.4. So that annotation, that @atomic at the top, is actually an annotation from us using our tool, marking that this method is supposed to be atomic. This is one of the bugs they found was this method actually in JDK 1.4 was not atomic. And the reason for that is line 1, it calls length on a string buffer, and line 4, it calls get value on a string buffer, but there's no synchronization. So in between those two lines of code, some other code might be able to modify the value of the string buffer and change the length, right? And so simplifying slightly, what our tool ends up noticing is that the effect of these first 4 lines is effectively non-atomic, which is the greatest element in the ordering on effects. And then every time it goes through a line of code, it checks, okay, is the residual of our current bound with this code we just checked the effect for still defined? And if it is, it pushes that down further. And so simplifying slightly so you're not staring at a residual of a residual of a residual of a residual, essentially what it notices is, well, the residual of atomic with respect to non-atomic. So what's left if you are trying to be atomic in behavior, but you've already done things that are not atomic? Well, that's undefined. And so it notices that on line 4, and so that's where we report the error, which is exactly, that's the earliest line of code in this example, where once you've done that, you've already broken this guarantee. It's already too late, you're not atomic anymore, doesn't matter what else is left in the code. And so this gives us a much more precise error location than just saying, well, it's somewhere in this line of code, right? Which for this method is not terrible because it's not too huge, but for larger code and certainly for more complex effect systems, it gets quite tricky, right? So wrapping up, the things we did in this paper are identifying this algebraic relationship between this sort of local and global views of traditional effect systems and how this sort of connects theory and practice, and finding a way to extend this to at least some flow-sensitive effect systems. We implemented it for Java. It's online. There's an artifact linked from the paper. And we validated this on some existing and new effect systems. So, thanks.
Okay, questions from the floor? Right at the back.
Thanks for your talk. So my question is, there might be multiple same effects in the global constraint. So how do you know if you have a local constraint saying X follows Y, then how do you know which Y is the one you want in the global constraint?
Yeah, so that's a good question. So for that simple example that I showed a few slides ago, there was only one trace. Like it was definitely, you wanted to do A and then C, and that was it, just to keep the example simple. But this theory works out even if your traces are sets of traces, because it turns out actually not just formal languages, but even regular languages, you can define this residual operation. That's also in the paper.
Okay, thank you.
Yeah.
Okay, any more questions? Okay, well, if there are no questions, I will ask a question. Your intriguing residuated semigroup /
Yes.
operator, that seemed to be a bit like an abductive
Yes.
operator, and it sort of reminded me of that work that Roberto did. I guess he's in the audience somewhere. When he had this. When he and his colleagues had this domain refinement technique, when you took an abstract domain and you added, you performed height enclosure, was it? I remembered. Okay, and that gave you this arrow which allowed you to do a form of abductive reasoning. So that seems to resonate.
That certainly sounds related. I'll have to look at that in more detail. It sounds cool.
Okay, any other comments or observations from the floor? Well, if not, we will thank our speaker, and perhaps the next speaker could set up.